My name's John Roberts. I'm a civil and structural engineer, and I've been involved in the designing of rides, including the Pepsi Max big one, for about the last 20 years. We had a specified height so that the ride would become the tallest roller coaster in the world. Height matters in a roller coaster because the height gives you the energy which is what propels the train around the ride. So if you want a fast ride, you have to go higher at the beginning, otherwise you can't have a fast ride. If you have a high ride, you have to have a long ride, because if you put the energy in at the beginning, you have to use it up before you get to the end. Otherwise, the train comes into the station at the end far too fast. The key design feature of any roller coaster is something called G-force. G-force is on a roller coaster. What does that actually mean? Well, people often talk about 4G, 3G. What it means is that you're being acted on by a force that's 4 times the normal pull of gravity, which keeps us standing upright and fixed to the surface of the Earth. So when you're in a roller coaster, and you're going around a bend at the bottom of a hill, just like that. Although the mass of your body is the same, there's no difference in the materials that make up your body, because you're being given a big G-force from going around a bend, centrifugal action, you actually weigh 4 times as much as you normally weigh. So if you were sitting on a spring balance on the seat of a roller coaster train, your weight would increase by a factor of 4 as you went round the bend. And in the same way, you go weightless when you're going over the tops of the hills. Now, what does that mean? Well, it means that roller coasters have to be designed in accordance with safe limits for G-forces for human bodies. Because actually 4G is just about okay for most people. 5G is a little bit uncomfortable. 6G is beginning to be very unpleasant. And at 7 or 8G, almost every passenger would come off with a nosebleed or with their eyes popped out of their sockets. Lots of different sorts of engineers are involved in these projects. For big roller coasters, there's 4 main types of engineers involved. Structural engineers who design the track, the bit that sticks out above the ground, and actually that's designed against wind loading is the main thing that you have to work against there. Mechanical engineers who deal with the train, the car, the bearings, the wheels and all of those sorts of systems. Electrical engineering, because this ride is powered by an electric motor which drives a chain which lifts the car and the passengers up to the top of the hill and gives it the energy. And finally, and very importantly, control engineers, specialists who are looking at programming the logic controllers which work out where the train is and give the instructions as to how to launch it and stop it. The early history of roller coasters was that they were built from timber. I mean, it was the available material, and in fact, every roller coaster until 1959 was built from timber, and they're still being built from timber now. But in 1959 in America, the first steel roller coaster was built, and that means that it had circular steel tubes which were used as the track on which the train runs. Up till then, the train had run on pieces of timber with little steel plates on. What the steel coaster opened up the opportunity to manufacture the tracks to much tighter bends, and also, crucially, you could start doing things like turning the cars upside down. So suddenly, within about the next 10 years or so from the introduction of the first steel roller coaster, we had coasters where you were turning upside down, where the trains were hanging below the track. Those are called suspended coasters. Then you can have the two together, so you could have a suspended looping coaster. And indeed, there are roller coasters now where you can stand up, so you don't even sit in a seat. You're standing up with your back against a post. All of those innovations came from the change in material from timber to steel and the increases in the structural performance that that brought. In a technical sense, the biggest challenges were that this is a very tall, very exposed structure, right on the edge of the sea. It gets hit by storm conditions which bring in salt and sand from the beach, so it's like the worst possible conditions for steelwork. A great deal of money had to be spent on what's called galvanizing and then painting the steelwork so that it doesn't rust. And just to throw in the final bad condition on this site, which had to be overcome, the foundations aren't terribly good here, the foundation conditions, and although it's built on what was a sandy beach, underneath the sand there's a layer of peat, which is very soft, soggy material, and we had to put a foundation through the peat down into the solid ground below. It's 65 meters tall, that's over 200 feet tall. It has a track length of 1.75 kilometers. That's over a mile of track that you go around. You go around it in less than a minute, so it's a very high-speed ride. There's over 2,000 tons of structural steelwork forming the track itself, and the two tubes that the train runs on only weighs 250 tons for the total length of the track. So there's much more structure holding up the track than the track itself. The steelwork was very expensive. The project was very expensive. More than 10 years ago now, it cost £12 million to build it, and it would cost over £20 million to build this again now. About 30 engineers worked on the design of the project, roughly half of them in the States and half of them in Britain, across all the disciplines of engineering. I don't just work on roller coaster and ride projects. I'm a structural engineer, so I work on other buildings. I've worked on the London Eye project, which is not anything like as high speed as this, but has very different design challenges. And I'm working on a big viewing tower at the moment that will be nearly 200 meters tall, which you'll go up in a capsule, have a look around and come back down again. All of these have similar engineering challenges. In fact, they all have issues of making structures stand up against natural forces like the wind and surviving weather and environmental conditions.